In this video, we'll discuss algebra and triangles. Now, some important properties are going to be helpful as we deal with this. First, remembering that the interior angles measured sum to 180, while the exterior sum to 360 degrees. It's also helpful to remember that the exterior angle measure will equal the sum of the remote interior angles, that the base angles and the legs of isosceles triangles are congruent, and that the Pythagorean theorem is only true for right triangles and trig ratios are also only true for right triangles. But that leads to a question. What about our other types of triangles? And we do have methods that can help us calculate some of these missing pieces in other triangles. One of those methods is called the law of sines, and we use this for non-right triangles. And when we use this, we have to remember that we are going to be talking about the opposite sides from a given angle. And often you will see this written as using lower script to represent each of those segment measures to make it a little bit easier to write into your problems. So the law of sines says that if we take the length of A over the sine of angle A, that will equal the length of B over the sine of angle B, which also equal the length of C over the sine of angle C. We can use any of those combinations to help us solve for what we're looking for. And typically what will be given is two angle measures and one side, whether that's angle side angle or angle angle side. And here's the thing to remember. If you have two angles, you have all three because you know they have to sum to 180 degrees. What we'll do then is solve for the missing side, and that's typically what law of sines is used for, is you have two angle measures, you're solving for a missing side. Now, when this happens and we have the two angle measures and we're solving for a missing side, that creates only one solution, and that's important because we're going to be talking about some ambiguous cases here in a minute. So when we want to solve these problems, we substitute in our measures, we're going to label each missing side that we're looking for, and then we're going to set up the equations and solve for that measure. And we can use the law of sines then to solve for the third side if we need or are asked for it as well. So let's say that we have triangle ABC, and we want to determine BC if we know that BAC is 77 degrees, ABC is 84 degrees, and AC is 21 centimeters. So first thing we'd want to do is draw our triangle and label the parts we have. So in this case, I can draw any type of triangle ABC, and then just label the pieces. And it doesn't have to be fully accurate as long as you get the right pieces in the right places. And you can see here I have my three measures, and I can say, okay, I want to solve for BC. So that's up here in the top left. And I can say, okay, I now can use my law of sines to help me set this up, because it will be the 21 centimeters over the sine of 84, and that equals this measurement BC over the sine of 77. Make sure your calculator is in degrees as you cross multiply here. And we're going to multiply both sides by the sine of 77 degrees. And depending on your calculator, you could just enter it just like this, or you can do the signs and use the answer key to help us go from one step to the next. And when we do that, we're going to just keep simplifying our expression on the left-hand side to determine the full value of BC. Now we can round it to the 10th and say that BC is approximately 20 and 6/10 centimeters. And if we need to find BA, we could do the same thing because we can then use the fact that the triangle has to up to 180 degrees to get angle C. Now there is this thing called the ambiguous case. And this happens when we are given two sides and the opposite angle of one of those two sides. And when we're looking and this happens, we're going to be solving for a missing angle, not another side. We have to solve for the missing angle. And that leads to one of three options. Either there will be no solution because it doesn't actually form a triangle, there'll be exactly one solution, or there's a potential that there could be two solutions. And that's the key we have to be very careful about with these problems when we have two sides and one of their opposite angles. So the first thing we do, like in the other problems, is we're going to substitute in our measures and label all the pieces we have. We're going to set up the equation and solve for that missing angle and realize that this will use the inverse sine function to solve. That's that sine raised to the -1. Now, if that inverse sine function tells us that the solution is undefined, that means there's no solution. In other words, that missing side would be too short for it to actually create a triangle. We don't have three sides that actually form triangles. But if it does work, we say, okay, the solution we found is one possibility, but we need to check its supplement. In other words, that angle plus what equals 180. If that supplement value creates a valid triangle with the other measure that's provided so that all three measures stay under 180 degrees, then we actually have two solutions. One that's going to be an acute angle and one that's going to be an obtuse angle. And both of those will be possibilities for the solution. So let's look at an example because I think that'll help quite a bit. Say we have this triangle GLM, and we are given that we want to determine the measure of LMG when we already know that the angle GLM is 41 degrees, GM is 16 feet, and LG is 18 feet. And you can see we have two sides and one of the opposite angles. So this is that ambiguous case because we're solving for the other angle. So we set up our law of sines. And we're going to say, okay, we're going to cross multiply here. And that's going to give us 16 feet times the sine of angle LMG is equal to 18 feet times the sine of 41 degrees. We can then divide both sides by the 16, and then we can put this in our calculator. And we're going to do the inverse sine because we now need to get the sine away from our measure angle. And if we just wait and do all that in the calculator, that's perfectly fine. Or you could change this to a decimal, and then from the decimal value do the inverse sine using the answer key. It's your choice. And that'll come out to approximately 47 6/10 degrees when you simplify that. Now that is one answer. So we know this answer is true. 47 6/10 degrees is a valid solution here. The question though is, what about its supplement? Will its supplement also create a valid solution? So let's try that out. If we say, what's the supplement to 47 6/10 degrees, we would be saying 180 minus the 47.6 degrees, and that's 132 4/10 degrees. And we have to say to ourselves, okay, we've got the 132.4, we have the known value of 41. If I take a third value, will all three add up to be less than 180 degrees? Well, the two that I have are only 173.4 degrees. That's less than 180. That last measure would just be 6.6 degrees. Yeah, it's really small, but it's still a valid measure. Since those two add up to less than 180 degrees, we know we actually have two solutions to this problem. And this is what the two triangles would look like. We have our one triangle here, and this is what that obtuse triangle would look like with the 132 4/10 degrees. Now, law of sines can help us find missing angles and the missing sides if we have two angles. The law of cosines is another option for finding sides and angles. And again, we're going to start with that same non-right triangle, the oblique triangle, and we have to be paying attention to the relating angle. In this case, for our equation I've written here in the generic form, we're using the relating angle of angle C. And then that tells us that the opposite side squared will equal the two legs that make up angle C squared minus 2 times those two legs times the cosine of C. Now, again, that's a longer formula, but it's going to be pretty flexible and help us solve for missing pieces. So if we have all three sides, we can calculate missing angles. Or if we have two sides and an included angle, we can solve for the angle measures or the third side. So there's a little bit more flexibility with how we use law of cosines. And as long as we have those two situations, we only have one solution. And there will be an ambiguous case just like there was for law of sines. So we just got to pay attention to what information do we have. If we have a standard situation, again, we substitute in our parts, we then set up our equation and then pay attention to how do we solve it. We may need to take a square root of both sides, or we may need to take the inverse cosine depending on if we're solving for a side or an angle measure. And if we need to find another side or another angle, we can use the law of sines then to help us because we'll have more flexible information at that point. Now let's look at an example. So here we want to determine what's the measure of KDH if we're given three sides. So we're going to relate everything from the law of cosines to this missing angle. So the side opposite is the 22 inches, and that's going to be our C value. So 22 squared will equal 12 squared plus 16 squared minus 2 times 12 times 16 times the cosine of the angle we're trying to calculate. So we're going to simplify this one step at a time. So we're going to square it, and then we've done our multiplication here. Then we can combine our addition. And now let's solve this as if this is solving like 384 times x, because that's really in essence what we're doing, trying to solve for that unknown. So we subtract the 340 from both sides. Then we divide both sides by the negative 384, which will simplify. And if it doesn't simplify, you can still just get that decimal and use the answer button as you're using your calculator. So whenever we're solving for a missing angle, remember we take the inverse cosine of both sides. So we're going to take the inverse cosine of the negative 3/8. And when we do that, it gives us 112 and then a long decimal. And if we're rounding to the 10th, that would be approximately 112.0 degrees. Now, like I said, there is the ambiguous case, that side-side angle, where we're given two side measures and one of their opposite angle measures. And when we use the law of sine or the law of cosines, when we have this situation and we're trying to find a missing side. So whenever we have the SSA for missing angle, we use law of sines. When we have the SSA situation and we want a missing side, we use law of cosines. And again, it gives us three potential solutions that we have to pay attention to. So like before, we're going to start with the measures we have. We're going to set up everything we can, and then we're going to rewrite our equation into quadratic form once we've simplified all of the expression. And remember, quadratic form is going to be ax squared plus bx plus c equals 0. That's going to be our quadratic equation. Now we can substitute in the values to the quadratic formula and solve the quadratic formula. And if we have no solution, if we get complex solutions, that means there's no real solution to this problem. That again, because the sides are not long enough. If we get two positive real solutions, then there are two real solutions to this. But if only one of those two solutions is positive, the positive solution is the only valid solution. Anything negative can't be true because you can't have negative measures. So let's go back to our case before that we use an example. But instead of solving for our angle GML, let's solve for side ML. And by doing that, we would say, okay, we're trying to find this missing side, but what we have in this problem is a relating angle already of angle 41 degrees, and we're going to use that angle to our benefit as we set up the law of cosines. So again, the opposite side from 41 degrees is 16 feet. So that's the 16 squared. Then we know that it's the two legs, lm squared plus 18 squared, minus 2 times lm times 18 times this cosine of 41 degrees. And so far, everything we have there can be simplified, and we're going to simplify it. Next, once we have the squareds, we can then say, okay, let's simplify this value here. And now let's rearrange our pieces by getting it into that ax squared plus bx plus c equals 0. So we're going to need to move the 196 over, and we subtract that from the 324. And then let's just change our order here to go from x squared to x to just the constant. Once we're in this form, though, we can use the quadratic formula. Remember, that's negative b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to use our calculators to help us with this. And our calculators, you can even do plus, and then you can say use that expression again and just change it to a minus and be able to do the parts. So we know the negative b is our middle term, and the opposite of negative is positive, plus or minus that b term squared. It's automatically going to become positive because it's being squared, minus 4 times 1 times 68, that's our c term, all over 2 times 1, our a term. And I can simplify it a piece at a time. And I can see, okay, the radical there became positive, so that's a good sign that there is a solution, at least one. And I then take the square root, and now I'm going to add the 2 and divide by 2, and I'm going to subtract the 2 and divide by 2 and see what happens. So I do them separately, and if I do that, I see that actually both of these values are positive, which means they both are positive solutions. There's two solutions to this problem, which is what we found when we did the law of signs ambiguous case example. And so we go back and we say those are those two triangles, 294 and 4/10 feet, as well as 2 and 8/10 feet. And those look exactly like what we'd found before, but we found that third side instead of that third angle.